I've seen the message on YouTube like 2 3 days ago, but I've not replied. Then the Thursday while I was traveling, he messaged me again on WhatsApp to tell me the Holy Spirit has been disturbing him to help the person. And I went to check the name and I realized that okay, it's genuine. And this person is in UK, and he said he also left Nigeria actually 2019, and he has been doing well in UK, and whatever he can do to help this person out, all the because he watched the person's YouTube video, oh, that this person used 8 years before she got nursing, and she has been extremely serious that she wanted nursing because that's her passion. So, and at the end of the day, I linked them up, so they've been talking, and one way or the other, he will send some dollars, and one way or the other, I just had to come in that, oh, this person has actually been going through a lot, one way or the other. By every means that he could help, he should try to help. And that's how it goes. That's how life goes. So this person has not, I said she's still in 300 level, she's yet to finish university, but probably immediately she finish, she can go to UK too. So all her years of struggle, she would have forgotten it. Someone can graduate at 23 years and suffer till 40 something. And someone can graduate at 30 and make it all at once. It all depends. It all depends. Do you have passion for what you are doing? So, and a YouTube video was up to like 40 minutes. So for someone to have sat down to watch almost 40 minutes video, that means that person must have been interested in whatever that person's decision would have been. And the person told me that if I have any nursing student or medicine student that are struggling, that are this, I should let them know. And all. So you never can tell where God is taking you. Just be passionate about what you do. Just be passionate. Don't always expect. God knows how to work things out for you. You just keep doing your best. Don't say, because I've seen it. Wherever Primax is going, I don't know. We just keep doing our best, the best we can do. So we don't really know where it's going. So we just keep putting up our effort and we keep trying. We keep trying. Nobody knows tomorrow. All of you now, we don't know how far you can go. So that's by the way. Please put up your efforts. If you have been writing jam, you have been trying and things are not working out, please, if you have passion for that thing, just keep fighting harder and keep trying your best. And I know God will work things out for you. Then a lot of time too, when they say speak, showcase, it's not like to mock you. If her video has not been on YouTube now, she might not. Some people might be feeling like, mo máa fail jam lẹ́ẹ̀mẹ́ta, màá wá sọ síta pé mo fail lẹ́ẹ̀mẹ́ta. Kìíní kan mi máa fẹ́ kéèyàn rí mi. She failed 8 times. She wrote it 8 times. And she was not scared to say it outside. And reasons why she wrote it 8 times, her challenges, her passion. Even if they want to give you anything abroad, those are the things they will look at. They will ask you to write your statement of purpose. So all of those things. So it's not everybody they give. You can be several nurses and they will just pick one nurse. All because they could see the passion. So, but let's move on. So today we want to quickly cover physics. So are you starting now? So let me share so we've covered physics, chemistry, and biology. So after the physics, we'll do chemistry, then we have a short break, then we'll quickly do our biology. So, link. I want him to have you started so I can share the link. So we are continuing on magnetism from where we stopped. So I want to quickly share the link. So please, let's let's maintain perfect silence, please. So far I've introduced you to magnetism. I've defined magnetism. I've talked about the different forms in which magnets exist. Abi? So then after that, I talked about the different terms we use when we're talking about magnets. So we define magnetism, and all of you know what magnetic materials are and the non-magnetic materials. Then after that, we talked about magnetic induction, Abi, the magnetic sintering, magnetic shielding. Do you still remember? Then after that, I started talking about the production of magnets, artificial, and we have natural magnets. And we say natural magnets are lodestones, right? Then we produce artificial magnets. Then I think that was what we did the last time, which was magnetization and demagnetization. On magnetization, I showed you the different modes in which you can produce a magnet. So please, let's keep quiet. So the different modes in which you can produce a magnet by stroking method, Abi. So we had a single and divided stroke. And I also did it by electrical method, in which we put the metal inside a solenoid, Abi. Then we produced a magnet. Then after that, I talked about properties of a bar magnet and magnetic field lines together. I said whenever a magnet is suspended, it's always lying in the north to south direction. So that is when a magnet is suspended. Then I also said something that the magnetic field line of force is the direction in which a magnetic compass or magnetic needle will tend to move, Abi, that the North Pole will tend to move. It's an imaginary line that the North Pole will tend to move. Then after that, I said like poles repel, unlike poles attract. Do we still remember that? So then after that, I said field lines, they do not cross, because if they are coming this way and they have the same field, they will repel. If they are going, they will attract, Abi. So it can go from north to south. So the field goes from north to south outside the magnet, and from south to north inside the magnet, to form what we call what? A closed loop. Do you still remember that? Then after that, I gave you the magnetic field patterns. I told you that magnetic field is always strongest at where? At the poles. So it is stronger at the poles. Then if you have the North Pole and the South Pole, we saw that the iron filings that we used, they clung more to the poles of the magnet, Abi. So we've done that. Then we also talked about uniform and non-uniform field, right? So a uniform field, you're going to have equal spacing of the lines, and they will go parallel, right? So then you have equal strength at every point. But for a non-uniform field, you have unequal spacing and you have different strengths. All these were the things I've talked about before, which was still the introduction to magnetism. Then in the last class, I talked about temporary magnets that gave us an electromagnet. And I told you that electromagnet has its application where telephone earpiece, electric bell, magnetic relay, loudspeaker, circuit breaker. So you need to know, they can ask you that, what's it called? Electromagnet is used in all of the following, except then they will write them out in probably Roman numerals. So you need to know that your electromagnet is used in electric. The principle at which they work is what I've explained with electric bell. So it's general. When electric current flows, magnet is produced. Then the magnet attracts a metal that either help you to do your job. So when it attracts the metal, it can be used to switch another thing. Let's say this is a switch. This is a contact that, normally if I want to switch this thing, I might have to press up and down. I want to quickly show you because I don't want to waste time on that. If this is the switch, if I press down, my light will come on. But let's say this switch now, if I touch it, it might shock me somehow, or the voltage is too high. So I need something that can help me to switch it. Then I can put up my electromagnet, then put out something like this there, so that when current start flowing in that magnet, then this thing, like a metal, just like that gong that was hitting that thing. So immediately that thing becomes a magnet, something around there. Then it will attract this. By attracting this, it will help me to switch this. So I didn't touch it. I went to switch somewhere, then current start flowing. Then that thing became a magnet. That's electromagnet. And that attracts like a metal that switch this. I didn't touch it directly myself now. That thing helps me to switch it off. And that's how magnetic relay works. So you use it to switch another switch. So we're going to draw all of those diagrams for better understanding again. So we have magnetic relay, we have circuit breaker that helps you to cut off electricity if there's a sudden surge that comes into the house. Then your telephone earpiece, someone speaks into the phone, then the sound is converted to electrical energy that runs through the coil and vibrates the diaphragm of the earpiece. And that electric energy again is converted to sound energy that you now hear in the earpiece. So all of those things, they work based on the use of an electromagnet. And I told you how temporary magnet is produced, and now a permanent magnet is produced. Abi? So I said permanent magnets are magnets that you don't easily magnetize. When you want to produce them, it will take time. But the moment you produce them, it becomes so difficult to demagnetize. Do you remember? So then for temporary, what do you use to produce permanent magnets? You use a steel. But for temporary magnets, iron. So they are easily magnetized. And the fact that they are easily magnetized also means they are easily demagnetized. So those were the things we have talked about so far. But I need you to note something. As from this moment on, we will start working on applications of all of these things. We will start what we call force on a current carrying conductor. And we'll start looking at things in 3 dimensions. And I need you to open your mind when I start showing you. So please, it's not so hard, but you will be asked questions in 3 dimensions. Then when I'm through, we'll try to solve all the possible questions before we now move on to chemistry. So far so good. This is 11 o'clock. Let's say we are using 2 good hours for all of these things. But before I go into that thing, let's look at magnetic field around most materials that we can talk about. So let's quickly look at magnetic field again, because we'll be needing them. So if you're talking about magnetic field, the first part, let me say a bar magnet. By now, all of you should have known how magnetic field runs around a bar magnet. Abi? By the time you draw your bar magnet, let's say this is north and this is south. How does it run? From north to south. Abi? From north to south. Then I say if I want to know the direction of the force, what do I do? I'll draw a tangent to the curve. Abi? That's what we said. So this is the field. It runs from north to south, but it runs from south to north inside the magnet. So this is the magnetic field around the bar magnet. Then for solenoid, how does the magnetic field looks in a solenoid? A solenoid is a coil of wire. And let's say I have a metal inside the solenoid. So for a solenoid, let's say the current is flowing this way. I on a current and the current starts flowing in that wire. Then it goes through the back, then it goes up and it goes up. So if I want to know how this is, I'm just trying to check something. So this coil of wire is called a solenoid. The magnetic field of bar magnet is exactly like that of a solenoid. So when you have a solenoid, a coil of wire, but how do you know which pole? Let's say this part of this bar magnet is A, this part of the bar magnet is B. If you want to know which side is north or which side is south, then you are going to use your right hand grip rule. So we're about to start. So to know the field now, to know the field, we are going to use what we call right hand grip rule. Right hand grip rule. So I want to know how the field will run. So you look at these currents. For now, let's just note this. How are they moving? Up, Abi. So this is your fingers. This is like the metal now. So you can grab the metal like this. Your fingers are pointing up, meaning that the field is what? Going up, Abi. So when you wrap your fingers around it like this, it means the field is going up. That's why I said we're about to start some 3D imagination now. So you have to pay attention. So now, if I grab the metal and I hold it like this, where is my thumb pointing to? To the left. Wherever your thumb points to, that is where your knot is. So if you're given a system like this and they ask you that what is A, what is B, you will look at these arrows. Then you use the arrow to grab it. Is that taken? Then when you grab it, wherever your thumb points to, that is called your what? Your knot. That means the other side is the south. Is that taken? Now, what that means that if the arrow had been going down, so if current start flowing now, let me change the direction of the current. Then I will have it go like this, then like this, like this, like this. So then to travel down like this. Then let's say this is A, this is B. So in that scenario now, can you tell me which one is north and which one is south? Eh? B is not, because now you are not, this arrow shows that point your finger like that, Abi, but this arrow shows that point your fingers like this. Do you get that? So if I hold this thing like this now, you can see it's going down, Abi. The arrows are going down. But if I hold it like this, the arrows are going up. Where's my thumb pointing to here? Left. So that means that north is here. But here now, as it's going down, where's my thumb point to? So that means north is here. Do you get that now? So this is the north. B is the north. YA is the south. But here now, A is the north, B is the south. So now, if this is north and this is south, how will the field runs? So the field always run from where? From north to south. So my arrow will be like this. So in case it is just the arrow they put and that line they put there, you can tell a lot of things. The moment you see the arrow going this way, then you already know that must have been north and this must have been south. I hope you are following. Then, but for this now, it's supposed to run like this. Why is my arrow going like that? Because the B part is what? The north. Do you understand that? So whenever you have a solenoid like this, I want to determine the field and the direction of the current, then you use your right hand grip rule. Is that taken? So you can see this is the magnetic field now. Then this is the direction of the current that is going. So, sorry. Another one is you can have a straight wire. They can ask you that how do you determine the field for a straight wire? I'm doing this first because you'll be applying them soon. A straight wire carrying currents. It's just like this guy. If you look at these circuits now, this is a straight wire, this is a straight wire, this is a straight wire, this is when it got here is when it became coiled. So if you have a straight wire and current is flowing in that straight wire, current I, and they ask you that how would the field look like? So now, for a straight wire, look at where the current is pointing. You are still going to use, let me give you the rules you are going to use. For a straight wire, you can use right hand grip rule. This normal rule. That's one. You can use clenched because they can ask you all of these things that to determine the electric and the magnetic field around the straight wire, what are the rules to use? So please follow. That's why I'm starting with physics, because you have to use your brain in all of these parts. So now you are going to use clenched fist rule. So you can use clenched fist rule, which is almost like your right hand grip rule. Then you can use Maxwell corkscrew rule. You can use a corkscrew rule too to determine the field. One thing I now need you to know here is that this is a 3D thing. Let me use my clenched fist rule, also called like the right hand grip rule. It's just like a fist like this, but with your thumb out. So in what direction is the current going? Up. So I want to know, how will the field around this guy look like? You are going to grip it. Let's say this is the wire now. You grip it. You can see where my thumb is pointing. That shows the direction of the current. So where would the field runs around? Look at my finger. Can you see? So the finger is wrapping this guy. So that means the field will keep going around this wire like this in a circular pattern. You know, I told you that we have to imagine things now. So it will go like this. So it will enter through here, come out through here, come through here. You can see this one is like it's coming out of the board. Then it goes this way. Then it goes inside the board. Then it comes outside. So I can draw it like this. So the field on this side is going inside the board. The field at the back, you know, if this you have to see because I'm drawing it on the board, so you might not really be able to imagine it. Who has like a rubber band? Don't lose your hair. Rubber band, please let me to pass one. Thank you. So this is the wire now that is carrying the current. Let me use the cap as the current. So the cap is facing up. I want to determine the field. So the field will keep going around the wire. So if anything is traveling around this rubber band now, how will it move? tí kọ̀ọ̀kan bá move, so that means pé it will enter here, abi, it will come through the back, come out of here, then go through this way. Can you see? But there's no way I can do this on the board for you to really see, except we use a 3D diagram on the board, which we can do that. But you will see a lot of things like this. So which means on this side of the marker now is going inside, abi. If you are viewing from here, it's going inside, abi. Then on this side is coming to the back. Then on this side is coming outside. So it's coming this way. Do you get that on this side? So, but instead of saying, oh, it's going inside, it's coming outside, you are going to note something. Every time you see dots like this, it means it's coming outside. Every time you see cross like this, it means it is going inside. We are going to apply that on this topic. Look at my arrow now. This marker, if I'm throwing it towards you, arrow means head. So this point now you can see is towards you. If I shoot an arrow, as the arrow is coming towards you, what will you be seeing? The dotted part. But if it's from the back, you will see this marker that is crossed. Abi? So if either I shoot the arrow now, as it's going away from me, I'm seeing cross. But you that is coming towards, you'll be seeing dot. So if it's coming out towards you, then you will see dots. If it's going away from you. So if I use that knowledge now to ask you this question, on this side, right and left, which side should be going away from you, going into the board? Which side should be coming out of the board? Left. So in your questions too, they will be telling you that it's going into the paper, it's coming out of the paper, it's going into the screen, it's coming out of the screen. You have to understand all of those things. So now, let me now redraw this one. As the current is moving up, I can simply just put something like this. And that simply tells me one thing. What does that tell me? On this side is going inside the board, which is like the Z. You know, there's Y-axis, there's X-axis, there's Z-axis. But the Z-axis is, let's say, Y up, X right. Z will be like inside. You get? So now that's the 3D. So now from what we have here, on this side is going into the board. That's what you will say. Or you will say it's going away from you. On this side now, it's coming out of the board. So you know, there's no way I can draw it here now. This is here. I can't draw what is coming out. That's why we have to use all these designations so that you get it with time too. Please, do you understand that? So now, whose band is this? Thank you. Oh yeah, everybody. Draw for this one. The current is coming down now. How would the field look like? And these things will be used to ask you questions. They will use it. They can put a paper there and tell you that in what direction would that paper be deflected and all of those things. I'm always ready. Okay. So you can use any of the, I will tell you how to use the corkscrew rule soon. So you can always sit if you want to sit. Oh yeah, what do we have? Somebody? So if you do your thumb like this, size your finger curly. You know, on this side is coming outside. Abi, on this side, your finger should be coiling back inside. Do you get that? So that means on this side, it will be coming outside, just to depict it. Or you can simply do your arrows like it's going. So meaning that it's going inside there and it's coming outside there. So wherever you see me do any cross like this, it means it is going inside. When you see me do the dots, it means it's coming outside. Please, do we understand that? So that's for a straight wire. Now let's look at a loop. A loop. All of these things we'll be applying them. That's why I'm taking them step by step so that you will understand it better when I start applying them on DC motor, AC motor, and the likes. Are you true? So let's see a loop. How does field looks in a loop? That's D. So we want to look at the magnetic field in a loop of a wire. So this is like a loop. Current is flowing in this loop. It might be the current, it might be the field. But let me first use the current to determine the field so that you see the diagrammatic representation. Normally, the moment you know the current, you know the face of the loop. Every loop has two faces, like that rubber band. So let me use that rubber band again. Sorry. I'll give it back to him. So are you through with the board? Can I explain? Wait. I didn't explain corkscrew. How many of you have opened and drink before? All this wine. You know, there's this screw that you can use to open a wine. So now, if you are even a boat, normally when you want to boat something, those of you that are like the engineers here, let's say this is a screwdriver, Abby, then you start knotting the screw and nuts. Do you remember? So by the time you want to lock it, you want it to lock. How do you always do it? This way, Abby. You'll be, as I'm doing this now, it will be tightening. It will be tight. As I'm doing this, it will be loosening. It will be coming up. You can't imagine what I'm saying. Like now, timber fed thing, timber fed lock it. If you want to lock tap, you always do it like this. If you want to open tap, you always do it like this, Abby. If you're locking screw too, you always do it like this. If you are bolting something, that's how you always do it. So if you want to open the wine, you can do this. Look at this now. You can see the marker. If I'm doing it like this, you notice something that will be coming up. I'm not the one pulling it up. Oh. My hand might not allow it to come up straight. Can you see that? If I'm doing like this, you notice something. Do you notice something? If it's your pen, you can try it too. So, which means that if I'm doing like this, it's going down. That means that when the current is going down, the field is always like this. Coming out from here, going in from here, like what we did here. So as I'm doing it like this now, current is going down, Abby. Then as the marker rotating, is rotating like this. Do you get that? Then if current is going up, you can see that the marker is going up now. As the marker rotating, is going like this. You know, I told you that we have gotten to a level that we start to imagine things. And if you cannot really imagine things, you can't really get this topic so well. Because it's not so difficult, but you have to start thinking beyond the ordinary. So you have to see things with your eyes, with your mind, and with your brain, not with the board. So, please, do you understand what I just did? So that's called the corkscrew rule. So you continue to turn like this, then it keeps coming out. Then that shows that the field is going like this, like this. Then you continue to do like this, then it keeps going in. So that shows the field is like this, like this. So that is what we call the Maxwell corkscrew. So you can use any of this rule to know the direction of the magnetic field when you know the direction of the current. And when you also know the direction of the magnetic field, you can also tell the direction of the current. So the moment you see that the field is like this, then you just grab it. That means it's coming out from here, then it's going in from here, then your thumb points up. Oyinbo, wake up, don't sleep. We are just starting. What's your name? Juliet. Eunice. Eunice, stop sleeping. So can we move on? So for a loop now, how does a loop work? The field, please, I'll just tell you something, just note something here. They can tell you that they can put a current like this and say this is a current. And they ask you that the field, what is the field inside the loop? They can also ask you that what is the field outside the loop. That's one thing. Another thing is they can tell you that what is the phase of this loop. Is it north? Is it south? Because all of these things apply. Look at this this guy now. You can look at it from this direction. If I look at this from this direction, just like this, everybody imagine this. So this marker, this thing now, this current is going in this direction. Abi, that direction, is it clockwise or anti-clockwise? Is anti-clockwise. So clockwise, so that is what, and it's going in anti-clockwise manner. But let me ask you to go and stay on the other side. Like now, as I'm holding this rubber band, me, I'm seeing anti-clockwise. My own arrow is going like this. But from your own end, if you look at that same arrow, you'll be seeing clockwise. If I'm looking from here, let's say my arrow is going like this, up. From my own view, it's going up. That means for me, it's going like this. Do you get that? But for you, it will be going like this the same way. But from the point you are viewing it, you are going to be seeing clockwise. But for me, I'll be seeing anti-clockwise. That means that for me, this part is a particular thing, either north or south. I'll tell you which one it is. For you too, you are seeing either north or south. We are not seeing the same thing. Me, I'm seeing north, you are either seeing south, or you are seeing north, I'm seeing south. So let's see what that is. For you to know which part you are looking at, that's the first thing. Let's determine the pole. For you to know which pole you are looking at, just draw your hand like this. This arrow here shows what direction? Anti-clockwise. So which means that this arrow that is going anti-clockwise, which face am I facing? That would be your north. So whenever you see that the current is anti-clockwise, that is your north for the loop. Do you get what you are saying? Please follow it. We will apply everything. When we get to electromagnetic induction, and I start talking about Faraday's laws of electromagnetic induction, how all of these things happen, the repulsion. Lenz law states that the direction of the induced current always work in order to oppose the motion producing it. All of those things will be applying these things. That's why I'm first explaining them first. Are you following? So now, this is going to go anti-clockwise, Abi. So now, if it's going anti-clockwise, this one is also going anti-clockwise. That shows north. But on the other side now, that means on the other side of the loop is going to be clockwise. So for south, it's going to be clockwise. So in order to determine the pole of a loop, the side that the current is anti-clockwise, that is the north. The side that the current is clockwise, clockwise, that is the south. So which means that this can be my south now. If the moment you can see that the current is going clockwise, and they tell you that what is the face of this loop, then you tell them that the face is south. The moment you see that the current is clockwise. I hope you're following. Then the moment you see that the current is anti-clockwise, and they can ask you this way now, they can say you are facing a side of a loop, and the current you are seeing is anti-clockwise. They now say that the side of that loop that is into the paper or into the screen is what? North is what you can see outside. That means what is inside the screen must have been south. So your brain must work with what they are saying. Do you get my point? The side that is into the board now for this guy will be what? South. Why the side that you can see out of the board is what? North. So those statements, you have to watch them. It's not going to be that difficult, but questions do come out every time. So can we move on? So now that we already know the poles, they can ask you the field. Inside the loop, is it coming out or going in? Let's check. We'll pick it. Emmanuel, don't give up. It's not over. So here now, in what direction is the current moving? The only problem you can have is if you don't know the difference between clockwise and anti-clockwise now, it's a problem. So this current is going what? Anti-clockwise. What is the face of this loop that you are looking at? North. That means the other side would have been south. And on the other side, that means if you are staying at the back of this board and you are looking at it, you will actually see clockwise. And that side must have been south. So what do I want to determine now? The field. Let's use the rule we use when we're talking about straight wire. Okay, everybody. When it is going up, I can just treat this one like a straight wire. Just grab it. That means inside this place now, what will it be? Is it coming out of the board or going inside the board? Coming out. Because when you grab it, your fingers will come out of the board. Abi, then on this side, it will go inside. It's a 3D thing. If this thing had allowed me, I'm supposed to be drawing circle like this. A part coming out and a part going in. So it will be like a field that is running round. Do you get that? So now, but since we can't do that with this now, what we can do is that we can just put dots, 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 and you already know what that means. That means here I can put cross, cross, cross. And in your question, they might not put all these dots, dots, cross, cross, because they can represent 3D with an image. So they might run the field for you. Your brain should just know what we are just simplifying it like this. If the current is here, what will this side be? What will this side be? B is what? Just always say outside the board or inside the board. For this now, you can either say outside the board or inside the board, and you can also say up the board or down the board depending on the direction. You can say to the right or to the left. So for this now, if you use your right hand grip rule, at B, what's happening? Coming out of the board. So it's coming towards you. Shebi? At A is going inside. So if they now ask you that, how does the field runs inside this loop? If you check everything, you see that everything is coming out. So, and what is the pole here? North. Abi? For anti-clockwise. So in the loop now, it's coming out from north. Arrows always go away from north. So it's like coming out in that place now. So you're going to have this place to be cross, dot, 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 dot. If you want to check, you can check. Let me just see if I can see a 3D image. Please, you people should not put heads on the desk. Don't get tired though. Don't get me tired. We are just starting. And that's why using times like this is better. A day like Saturday like this. So you express yourself. That's all these things. Tó bá lọ ń ṣe ní late kínní. So look at this image now. For this one, what I'm seeing here is that, look at the arrow here. You can see this arrow shows that it is clockwise, abi? The arrow shows that it is clockwise. But if you look at the field, how is the field going? If it is clockwise, then that means it will be going inside here, abi? This one will be going, this one is anti-clockwise, what we have drawn. This image I'm seeing here. So you can see that they are also using a plane just to show you. So on this side, the field is going inside. On this side, the field is coming outside. So in your question, they can put something here like a marker. They can tell you that something is placed on this pin. In what direction will that pin move? It is the field that will move it. So they will not tell you that. Imagine I place, let's say I'm just giving you a question and I say, and there's a piece of paper that is placed on this side of that material. And I tell you that in what direction will this piece of paper move? Then you will tell me that, oh, it will, the paper will be pushed out of the board. That's your answer. Because the field is pushing, no, inside, sorry. The paper will be pushed inside the board. Do you get that? Because the field is moving inside. Please, do you understand that? All of these things are questions that they can ask you. So you can just check a 3D image of magnetic field in a loop. Then you will see that diagram. But for simplicity is what I've done here. Everybody, imagine the arrow is here. If the arrow is there, how will it have been? If the arrow is here, it will still be outside there, Abi, and inside there. Do you get that? That means all in this loop, the field is coming outside. Then outside the loop, the field is going inside. It's as simple as that. So you can do that for clockwise. Oh yeah, do for clockwise. So tell me what the field is going to look like in the loop. So now you will start hearing inside, outside, up, left, right, all of those things. We'll try to solve some questions when we are through. That's for a loop. Then we'll start first on a current carrying conductor. But before that, I would like to quickly explain Earth's magnetism in a simple manner, in a very simple manner. I'm not going to. Are you true? I got my eyes on you. The rain is falling down. The rain is falling down. The rain is falling down. Are you true? Can we move on? So let me just show you this one, but we might not talk much about it now for the Earth. So Earth's magnetic field is just taken as a uniform field that runs from north to south of the magnets. Even though Earth has geographical north, geographical south, east and west. We're going to talk about Earth's magnetism soon. So quickly, so that we can finish magnetism before we move on to chemistry. So this one I want to talk about is Earth's magnetism and the elements of Earth's magnetism. So with simplicity, there are a lot of things that confuse people on this Earth's magnetism. But in order not to bring in the confusion, I just want us to understand it in a simplified manner because it answers all your questions. So the Earth itself, this our Earth, behaves like a magnet. As if there's a giant magnet on Earth that attracts everything to itself. It's still different from Newton's laws of universal gravitation. But the Earth itself behaves like a magnet. So let's write some things. Let me just give you a short note on that. Are you ready? Right. The Earth behaves like a giant magnet. The Earth behaves like a giant magnet, and this can be traced to several reasons. This can be traced to several reasons. The Earth behaves like a giant magnet, and this can be traced to several reasons. But the most important reason can be traced to the molten metals. The most important reason can be traced to the molten metals. Molten, M-O-L-T-E-N, molten metals found on the Earth crust. Molten metals found on the Earth crust, which are in motion, or which is in motion due to the rotation of the Earth. Which molten metals found on the Earth crust, due to the motion, or due to their motion, what did I say there? Which is in motion due to the rotation of the Earth. Which can give electric currents. Full stop. The production of electric current is associated with magnetism. The movement of charges or the production of electric current is associated with magnetism. According to Oersted, there was a scientist that told us that moving currents produce magnetism. According to Oersted, this man said when you have a moving current, so this moving current generates magnetic field. A moving current generates magnetic field. Full stop. So that's just an introduction. There's a lot to say about Earth's magnetism. But just for you to know, in case they ask you, that why does Earth behave like a magnet? I showed you something the other time, that if we have a straight wire and straight wire is carrying current, if there's no current in this wire, there will be no field. If there's no current, there will be no field. But the moment current starts flowing, field will be generated. So a wire can behave like a magnet. Why is the wire behaving like a magnet? Because as current is moving, magnetism is generated. You will see how it behaves like a magnet soon. You will see. So, which means that anytime there's movement of currents, and current is due to electric charges, those of you that have started electricity, you have electric current when there is flow of what? Electric charges. So on the earth, there are some metals in deep earth crust that are molten, just like electrolyte. And the earth continues to rotate. As the earth is rotating, these charges are also moving. They are rotating. And when there's a flow of charge, there's flow of what? Electricity. And if there's electricity moving, there's what? Magnetism. I hope you're getting my point. If electric current is moving, there's magnetic field. Abi, this is magnetic field. If current is moving, there's magnetic field. So if the earth is also rotating, and there are some metals deep in the earth crust, as a result of the earth rotation, those metals that are molten too, they are also moving. And for the fact that they are moving, there will be current flowing on the earth. And as current is flowing on the earth, that means there will be magnetic field created. Rotation of the earth. Rotation of earth makes molten metals to move. And when molten metals move, that means charges are what? Charges are moving. And when charges move, there is electric current. And when there is electric current, then you are expected to have what? Magnetic field. I just summarized all the whole stories. So as the earth continues to rotate,